In this video, we're going to take a look at wave behaviors. And the reason we do that is because a wave, unlike normal matter where there's certain things that we kind of expect to happen, waves are things, but yet waves are not matter. They're just a disturbance of matter. And so we're going to take a look at some of these behaviors or properties of waves. And the first thing we're going to look at is reflection and transmission. Waves reflect and transmit. Now, what that means is that they bounce off of objects, and that also means that the wave will continue through a medium if it encounters something. And you would have experienced this if you put your ear up to the wall and you can hear somebody talking on the other side of the wall. The sound wave hits the wall, and then some of the energy of the wave reflects off of that wall, but it is also transmitted to your ear on the other side of the wall. The second thing that we can look at is that the waves can overlap. And basically what we're saying when waves overlap is that, well, these two things can occupy the same space at the same time. Something that matter cannot do. And if you've ever had an accident, then you know exactly what I'm talking about. Two objects cannot occupy the same space at the same time. And then the third thing we're going to look at is such a big category that we're going to dedicate a whole video to this, but waves can also stand still and not travel, and they call those standing waves. Let's take a look at reflection and transmission. The best way to show you this is with the PhET simulator, so let's go ahead and check that out now. Okay, so what I'm going to do is create a wave pulse, and in this situation we're going to have the right end fixed to a C-clamp so that it cannot move. And I'm going to create the wave. This is in slow motion, and that wave is going to come all the way over and it's going to reflect. Now at this point I want you to answer the question. When it reflects, is the wave upright in the current orientation, or is it inverted? In other words, it's upside down. Alright, let's play this and see what happens. So one step at a time. So far so good. It's on its way up. But then it's inverted. Okay, so a wave pulse, which is traveling along a string, and it reaches a fixed end, is going to become inverted. Now, the question is, why does it become inverted? Well, the reason it becomes inverted is because of a third law action-reaction. As the string approaches the C-clamp, the string pulls up on the C-clamp, and the C-clamp pulls down on the string. And that's what I'm going to show you here. Everything is moving in the up direction, and so it's inertia which is causing it to go up. And as it goes up, it's going to pull on the C-clamp through the green dot, the green bead. And the C-clamp, because of Newton's third law, is going to pull down in the other direction. Alright, now let's take a look at what happens whenever it's a free end. In other words, it's free to move up and down. So we're going to do the same thing, and I'm going to make a wave pulse which points upwards, and I want you to predict right now, do you expect that wave pulse to reflect upright in its original position, or would you expect it to be reflected inverted where it's pointing down? Okay, let's give it a shot. So it's upright currently. And now it reflects in the upright position. So, the big question is, why does it reflect in the upright position? And the reason for that is actually quite simple. because the bead of string, or the string of beads, doesn't have anything to pull up against for that something else to pull down on the bead, right? Again, this is third law. So the bead has to pull up on something, and that something has to pull down on the bead. Well, there's nothing pulling down on the bead, so there's nothing to cause the beads to want to go in the down direction. There's nothing to change their direction. Now, it's not possible for me to show you transmission through FET, so we're just going to have to discuss what is going to happen with transmission. And so basically what we have is a wave pulse traveling along a string. And that wave pulse, or I'm sorry, that string is attached to a heavy section of rope. It's currently moving in that direction. Now, when the pulse reaches the string, just like with the C-clamp, is going to pull up on the rope, and the rope is going to pull down on the string. So what's that going to mean? Well, because the rope was pulled upwards, it's going to now have inertia in the up direction. And because the string was pulled downwards, it's going to have inertia in the down direction. And so what we end up with is a wave which is much smaller on the string, and it's also much smaller on the rope, and they're opposite of each other. Okay, so the wave on the string is moving to the left, and the wave on the rope is moving to the right. Now, remember that this is inverted because the rope behaved basically as the C-clamp. It was able to pull down, and the amplitude is significantly decreased because some of the energy of the wave got transmitted into the rope, but some of the energy of the wave stayed on the light string with that original wave pulse. So some energy is transmitted, some energy is reflected. Now, there's another topic that we need to look at, and that's two-dimensional waves. We're not going to do a lot with these, but I want you to understand the geometry of them. If you have a point source, a vibrating point source, it could be something like, dropping rocks in a pond at a steady rate or something like that. Then what you're going to create is a wave that travels along a circular arc. And these lines represent the wave crest. So if you were to look along this line from the side, along that line from the side, this is what we would see. We would see, remember, this is a crest, so here's our point source. We have our neutral position here, so we have a crest and then a trough, and then a crest and then a trough, and then a crest and then a trough. And at each one of these crests, we draw our line. Okay, so this is a side view, and this is a top view. All right, now what is the direction of wave travel? The wave, now these are called wave fronts. Let me be clear about that. This is called a wave front. The direction of travel is always perpendicular to the wave front. So this wave is actually moving in two directions, not just one, and hence it becomes a two-dimensional wave. Each one of these bright lines is a wave crest, and just so that we're perfectly clear on this, halfway between each one of these curved lines is the trough. All right, so we would be looking at that there. It's exactly halfway between. All right, now when you get far away from the source, then the wave fronts have such a large radius of curvature that they appear to be straight lines. We can also create plane waves which have no curvature to them by putting a block in, say, water, and that block is flat on the front, and we make that block vibrate back and forth. Well, that's going to create waves which are flat, wave fronts which are straight, but they're going to curve around the edges like this. All right, and so the direction of our wave travel is going to be perpendicular to the wave fronts, but this is primarily what we're interested in here. Okay, so that's the direction the wave's going. That's the velocity for the wave. Now, the last thing I want to mention here when it comes to reflection, and that is that we have the law of reflection for waves. And this is going to actually be valid for all types of waves. But basically, if we look at the wave fronts coming in, they're coming in at some angle like this. All right. Those wave fronts are represented by this single ray that comes in like this. Oops. It's not a good location for that. These wave fronts come in by a single ray that looks like this, and it's going to reflect off in that direction. Okay, now, this angle between the normal of the surface, this is the normal of our surface, it's a vertical line, it's perpendicular to the surface. This angle here is referred to as theta incident, and this angle here is referred to as theta reflected. Theta incident is equal to theta reflected, and that is the law of reflection. So that's about all you need to know for now about wave reflection. Now, the other thing waves can do is they can overlap. And in the world of physics, we call that superposition. And basically, that's whenever these two waves are occupying the same space at the same time, what's going to happen. All right, so two things can happen. We have constructive interference, and then we have destructive interference. With constructive interference, it's just what the name implies. It's a building up. So if I have two wave crests traveling towards each other, one goes this way, one goes that way. When they reach the same point in space where they're overlapping, then what we have is this. We have one wave crest. This is the one traveling to the right. Then we have the second wave crest, which is also traveling to the left. And when these two waves overlap, basically we're doing one plus the other, then what we get is a single wave pulse with twice the amplitude. So each one has an amplitude of A, but this is an amplitude of 2A. Hence constructive. Destructive interference is going to be just the opposite. You're going to have a wave crest approaching a trough, and again, each of them have an amplitude of 1. And whenever they overlap, we get the crest plus the trough. We add them up, and we get nothing. We get a straight line. Now, this doesn't mean that the wave has been destroyed. It just means that for this instant of time, there's no disturbance in the medium. All right, so now we're going to use the PhET simulator to show constructive interference. And as you can see, these two waves are now both pointing in the same direction, and they're approaching each other. Watch the amplitude. We have approximately twice the amplitude. Okay, so that was constructive interference with wave troughs. We can do this again with wave crests. and right there it is. Okay, so we get a building up of the amplitude. Now, the kind of waves we deal with are called linear waves. And simply put, that just means we're going to be able to add up the amplitudes one to one. So if I have an amplitude of 1 on a crest and an amplitude of -1 on a trough, they add up to 0. And if they're both pointing in the same direction, they would add up to 2. Okay, now let's take a look at destructive interference. Now, when these two waves pass each other, they should completely cancel out for an instant and then continue to travel as though nothing at all happened. And there it is. We had the trough, it was coming towards the left, and now it's going to continue to the left, and the crest is moving towards the right. Now, when it comes to waves and interference, there's a term that you sometimes hear called phase. And phase simply describes the relation between a crest and a trough. And when you have constructive interference, you're said to be in phase. And whenever you're out of phase, you destruct. In the next video, we're going to take a look at standing waves.